So let's run the test on our circuit. So we're going to open state that it is ready. Okay, so then here we will check everything that we have been checking so far: DC operating point, AC, pole 0, noise, and then I added something else that it is called the transfer function or XF simulation. And the XF simulation, it is extremely similar to an AC simulation. The only difference is that it calculates the transfer function from different voltage or current sources to only one point in the circuit. So the AC simulation, on the other hand, does exactly the opposite. It calculates the transfer function to all points in the circuit from one voltage or current source. So this is very handy because I can configure the XF simulation separately from the AC, and what I'm going to do it is just to extract what is the transfer function from the power supply to the output, because that will allow me to calculate the power supply rejection ratio. So the configuration is quite simple. You just have to enable the XF magnitude to 1. So you put it 1 here and get it enabled. And the rest is just in the XF simulation. Same configuration as for the AC simulation. You just select the node that you want to calculate the transfer function, and then typically that will be the output voltage. And that's it. So we're going to run the simulation. Okay, let's see. And then we are done. And well, we do pretty quick check. We check the gains that are exactly as the things that we want. The bandwidth, we see it, what is the bandwidth of our circuit. In this case it is around 8.5 megahertz for this circuit, and then we check the position with the poles and zeros. Of course, we bring also the zeros here, and then we see that they are more or less in variable positions. And then we can check the power supply rejection ratio, and then for that one I have already saved it in dBs. You can bring it from the results direct plot, main form, and then XF, and then just add the output in dBs, and then you have to select which voltage in the schematic. You just select this one, and then it gets added. Okay, it has been added. So, and then we have here what is the gain from the power supply from VDD to the output voltage, and we see that at very low frequency it is minus 78 dBs. So it is very good. So that it's any variation in the power supply get basically mitigated strongly by the circuit. So it is only appearing very little variation at the output. Okay, so we have this typically this curve, it is extremely low at very low frequencies, and then start deteriorating at very high frequencies, because it's basically no gain anymore that can filter the variations, and it may even get positive at the extremely high frequencies. But at extremely high frequencies we have that the power supply is normally filtered. So now we're going to do very quickly it is that we're going to demonstrate what happens if we don't use band gap reference or control voltage that from another part of the circuit. We're going to use this diode connected transistors here this row of transistors to generate the voltage, and then we're just going to tap this one here. And then let's annotate the DC node voltages so you have an idea of what are the voltage levels here. So this is around 840 millivolts, so let's say that it is close to what we need. We just save it and let's run the same simulation. And then we see that it is totally different now. So the power supply radiation ratio has changed a lot. So there is very little attenuation, and then we can see here that directly that any change in the power supply, these are diodes, so it is coming directly to they work like almost like a voltage divider. So any variation here is propagated directly to the voltage reference, and at low frequency the capacitor really doesn't work at all, so it doesn't help, and then it just deteriorates and even get amplified at relatively low frequency. Even get amplified that variation in the power supply. Okay, but sometimes we use this. It's just simple to implement, and if the power supply is very well controlled, then and it is very clean, then might be possible to use. Okay, so let's take a look to the noise of this circuit. So let's go to print noise summary. We're going to check the output noise, integrated noise in the whole band, whole type of noise, and the 10 first contributors. And then let's take a look to the circuit here. The first contributor is M5. We search for M5, and then we see already that it's something that it is not good. We have said that the input devices are those that should dominate the noise of the amplifier, and then we already see that we have violated that rule. So we have the bias in the current source, the one is contributing with is the main noise contributor, and for a large margin. So it is 33% coming from M5, and then the next one, it is M8. M8, it is here, and it is also the current source, the biasing, and it is contributed with almost 30%. And then it is only afterwards M1 and M0 and M2 are contributing. M0 and M2 are the differential pair. So as we can see, we can probably get a little bit better by increasing the length of the transistors and reduce their transconductances, but probably it's just going to work at some point. We're going to try exactly the same thing with the other circuit. Okay, so we can close this one. And the total noise 4.3 millivolts at the output. And yeah, remember that we have around 8 megahertz here of bandwidth. So we close this, and then we go to the other circuit here. We launch ADE. We're going to run exactly the same simulation, and then I have not added XF simulation here. Let's add it very quickly. 0.001 100 megs, and let's take 30 points per decade. We select the output node, and that's it. And then here we need to configure the voltage source so that XF simulates the transfer function. And I think we are settled. We run the simulation, and then we can plot the transfer function and dBs to output, and then we select the voltage source. The voltage source is this one, and then it's already here. Okay, let's run it again. Okay, so we have all the same simulations, and then, well, here we can see that we have the amplifier working without any problem, and then the bandwidth, the 3 dB bandwidth is slightly lower, and the reason is that we have another pole here that it is basically contributing to the number of poles in the system, and then needed to be changed a little bit the compensation also to avoid some peaking there. On the other hand, even though the high frequency value has changed a little bit, the noise performance we expect to be a little bit better. So let's take a look. We can put it from here of noise summary, and the voltage integrated noise 0.01 100 megs all, and then we see that the main noise contributors are the transistors and the differential pair, as I expected, and then the third noise contributor is the current here, and then it's M13. But M13 should be here, the current mirror here. Okay, so this circuit, we have that the input differential pair dominates the noise performance that it is supposed to be, and the same thing that we did before. Now we have the power supply rejection ratio of this circuit is at low frequencies around minus 80 dBs, and then start deteriorating slowly. So it is around minus 60 dBs up to like 10 kilos or around 5 kilos, and then it starts going up very quick. But it's typically behavior of the power supply rejection amplifiers. Okay, so this is our circuit, and now we will have to move this circuit to a block and start testing with more comprehensive tests to make sure that it achieves all the specifications. Among other things, we will start replacing ideal passive components from real components in the design kit. So let's start doing that.